In class 79, we were starting to use Snell's law, which allows us to calculate angles of incidence, angles of refraction, and indices of refraction. So looking at this image here, just to try to help you visualize this first material on the left-hand side, you could pretend, just for argument's sake, that this is air. That has an index of refraction of 1. And on the right-hand side, the colored glass, we'll say that this is flint glass with an index of, we're going to use the reference table for this, not necessarily the chart I have here. I'll update that in future classes with an index of 1.66, again, according to the reference table. It's not a huge difference. The fundamentals are the same using those numbers. We'll just get slightly different answers. Also on this, we see theta 1. What we call theta 1, we call that the angle of incidence. Notice how it's referenced to the imaginary normal line. Theta 2 is the angle of refraction. Again, it's referenced to the imaginary normal line. So theta 1 is angle of incidence. Theta 2 we call the angle of refraction. So N1 is always the first material we're traveling in, so the first medium. N2 is our second medium. So the way we put it is you're always going into N2. So if it ever says you're going into flint glass, you know that that's your N2. In this image, we notice that theta 1 is definitely bigger than theta 2, which tells us that N1 must be less than N2. If theta 1 were smaller than theta 2, then N1 would be bigger than N2. Okay, now Snell's law tells us that mathematically. It's a little hard to see using Snell's law, but it says that N1 times sine theta 1 equals N2 sine theta 2. Basically, what this relationship will show us is that if you have a larger n value, that'll be associated with a smaller angle. So let's see how this equation works. So in the image above, a ray of light in air is incident upon a layer of flint glass at an angle of 19 degrees. Label the 19 degrees on the diagram. So that 19 degrees is going to go up here, 19 degrees. Will theta 2 be greater than or less than 19 degrees? You can tell just from the picture that it's going to be less than. But another reason you could say it's going to be less than is, you know, this is a low n to high n problem. We go from a low index of refraction to a higher one. We know that the ray of light is going to bend toward the normal. So it's going to have theta 2 is going to be smaller. So what is the angle of refraction? A lot of students that struggle with these questions only struggle with them because they don't write their givens down. So you have to read the question carefully, get your givens straight, get your unknowns straight, and it's very straightforward from there. So you know right away that you're looking for theta 2, that's your unknown. So let's read the question again carefully. A ray of light in air is incident upon a layer of flint glass. So our first material is air, that's N1, 1. Our second material is flint glass, N2. And as I said, we're going to use the value from our reference table, not the one from this table. So that's going to be 1.62. Or excuse me, 1.66. And it's incident at an angle of 19 degrees, so that's theta 1. So the toughest part is just reading the question. I can't emphasize that enough. The only students who generally struggle with this topic do not write their givens down. So using Snell's law, N1 sine theta 1 equals N2 sine theta 2. So N1 is 1 times sine of 19 degrees equals N2, that's 1.66, sine of theta 2. I'm going to go through the algebra quickly. Just don't forget that you have to use the inverse sine to get theta 2, but theta 2 comes out to be about 11.5 degrees. Does this agree with our prediction? Well, let's see, is theta 2 less than theta 1? Theta 2 is definitely less than theta 1. Theta 1 was 19 degrees. So yes, it does. So reading number 4 says light travels from zircon into Cornoil. The light in zircon contacts the barrier at an angle of 20 degrees. So again, almost every student that asked questions about this in class wasn't listing their givens right away. That would be the first thing I do. I wouldn't do anything else until I parse through this, figure out what's N1, what's N2, theta 1, theta 2, what do I know, what am I looking for? So light travels from zircon into Cornoil. So you always go into N2. So Cornoil is our N2. And zircon is our N1. The light in zircon contacts the barrier at an angle of 20 degrees. So if zircon's our first material, that means that that is our theta 1. So when students in class were asking questions about this one, the first thing I said was you have to determine N1 and N2. And you have to determine if that angle is theta 1 or theta 2. The problem becomes much easier once you establish that. So as light enters the Cornoil, will it bend toward or away from the normal? Let's see, this is a high to low problem, right? High n to low n, 1.92 to 1.47. So we're going to say that this is high to low. Therefore, it's going to bend away from the normal. So if it's bending away from the normal, theta 2 is bigger. Another way to think about it is if N1 is bigger, that means theta 1 is smaller. So some people really struggled with drawing the pictures for this. So I encourage some people to just do the math first, then draw the picture after. So we'll do the math first. N1 sine theta 1 equals N2 sine theta 2. N1 is 1.92. Sine theta 1 is sine of 20. N2 is 1.47 times sine of theta 2, that's our unknown. In this one, solving for theta 2, we get about 26.5 degrees. That's our angle of refraction. So does this agree with our prediction? Well, we predicted that it would go away from the normal. So we predicted that theta 2 would be greater than theta 1. 26.5 is greater than 20, so yeah, it does agree with our prediction. So looking at number 5, again, you got to get the givens done right away. Don't do anything else before you go through this first sentence. So light refracts at an angle of 43 degrees. So right there, that's telling you that theta 2 is 43 degrees. How do I know that's theta 2? That's the angle the light refracts at, hence the angle of refraction, as it travels from air into quartz. So the first material is air, N1 is 1, and it goes into N2, so it goes into quartz. So N2 is, we're going to use the value on the reference table of 1.46. If you actually don't use that value, it won't work. Is the angle of incidence greater than or less than the angle of refraction? Explain. So let's see, this is a low to high problem. Again, why is it low to high? Because we're going from a low index of refraction, air, which is 1, to a high index of refraction, quartz, which is 1.46. So if we're going from low to high, we're going to bend toward the normal. So our angle of incidence is going to be greater than our angle of refraction. Using low to high, the wavelight's going to get closer to the normal, so the angle of refraction is going to be smaller. So therefore, theta 1 is greater than theta 2. And one way to think about it is if n1 is smaller, that means theta 1 is bigger. So let's see how we do here using Snell's law. N1 sine theta 1 equals N2 sine theta 2. So N1 we get 1, sine theta 1, that's our unknown. N2 we get 1.46. Sine theta 2 we get 43. Solving for theta 1, you should get about 85 or 84.5. Now a lot of people were getting 90 for this because they were rounding too early. Remember, I don't really care about significant digits, but you really aren't supposed to round until your final answer. If you round too much too early, you're going to get 90 for this, but 84.5 is a very different answer than 90. So watch out for that. Does this agree with your prediction? Yeah, theta 1, 84.5 is greater than theta 2, 43. So yes, it does agree. I just realized we forgot to draw images for our problems, so we'll go back to number 4 for just a second. So here's the classic way I'm going to draw these. I usually draw the interface between the two materials as a vertical line, and then I draw the normal line next. I always put N1 on the left, so I'll just write N equals 1.92 over here, and N2 is 1.47 over here. And then you don't really have to measure this next part, I'll draw it in a different color, but the sizes should be relative to one another. So if theta 1 is smaller than theta 2 as it is in this one, then your angle of incidence should be smaller than angle of refraction. So I'll draw one kind of like this. Here's my angle of incidence. I'll label that as 20 degrees. My angle of refraction should be a little bit bigger, so I'll exaggerate it though, something like that. We'll say that that's 26.5 degrees. So that's what I'm looking for the image. Going back to number 5 for a minute. Again, starting my image the same way. Vertical line, imaginary normal line. On the left-hand side, I have air, which has an index of refraction of 1. On the right-hand side, I have quartz, which has an index of refraction, again from our reference table, of 1.46. So theta 1 is 84.5 degrees, so that's a huge angle relative to the normal line. So it looks something like this. And our angle of refraction, again, we're going from low to high, so it has to be closer to the normal, and it's 43 degrees, which is something like that. So that's how the light travels from air into quartz. Now we're looking at number 6, the final one. So light travels from diamond into another material. So right away, you know that diamond, N1, is 2.42. Into another material you don't know, that's your missing material, so N2s are unknown. The angle of incidence, theta 1, is 32 degrees. The angle of refraction, theta 2, is 46 degrees. I don't even know what the question is asking for yet, but I have a lot of information already. So let's see, the other material must have a blank index of refraction. So if we're getting farther away from the normal line, so if theta 2 is greater than theta 1, then N2 must be less than N1. So it has to have a lesser or smaller index of refraction than diamond. So setting this up, N1 sine theta 1 equals N2 sine theta 2. So N1 is 2.42, sine of 32 degrees. N2 is our unknown, sine of theta 2, which is 46 degrees. I think N2 comes out to be about 1.78. Not checking that on my calculator though, but you can check my work. It should be pretty close to that if I remember correctly from class. So to draw this one, what does it look like? Well, we're going to start with our line between the two materials, then our dotted line, our imaginary normal. On the left-hand side, we have diamond. That's N equals 2.42. That's our higher index. And then over here, our N equals, I think it's 1.78. All right. Then drawing, we have to make sure this is sort of to scale. Our angle of incidence is 32 degrees, so that might look something like this. Our angle of refraction is 46 degrees, so that's something more like that. Actually, that kind of looks like a straight line. We'll exaggerate it a little more, something like that. This is 46 degrees. All right, and that's our introduction to Snell's law. It's a little tricky to get the image down. I understand that, understanding which one of these two lines here is the interface between the two materials. It's this one here and the normal line. Then drawing the light and knowing which angle, that comes with time and practice. But drawing images of each problem you do, I think, is the best way to do it. A lot of students I noticed in class were using this angle here. We never use that angle. It's always measured relative to the normal line. And we might see some problems in later classes where we orient this the other way, where our interface between the two materials goes this way and our normal line goes this way.